Okay. All right. So for exam 4, we're going to have chapter 6 and 7. We've got 2 class periods to cover those 2 chapters. So we can spend all our time on chapter 6 today. Chapter 7, Tuesday. Then the following Thursday will be a review. So I think we've got plenty of time. We can take all the time we need. Okay. So we're up to chemical reactions. This is just an introduction. But we will learn how to balance chemical reactions in this chapter. We won't learn it from the authors, though, because most chemistry textbook authors just tell you to balance by inspection, which means basically nothing. So I'm going to show you how to do it in a methodical way that hopefully will be less painful. So how do we know a chemical reaction has occurred? Up to this point, we've just been studying elements and compounds and how to talk the lingo. But what are some clues that a reaction is taking place? That is, substances are being changed from one form to another. They're usually indicators. Well, most of them have visual signals. Well, a lot of them, I shouldn't say most. A lot of them have visual signals. So what would those be? Like change of color. See that change. You might see fizzing. You'll see bubbles produced, gases. I'm sorry? Smoke. That probably wouldn't be a good thing. You might see, if you mix 2 solutions together, you might see a solid form. That's another indication. But they're not always visible. So you've got these possibilities: color change, solid form, bubbles. You might see the smoke, and if it's a controlled environment, that may not be so bad. But you might feel heat coming from the reaction vessel, or it could get cold, because some reactions go the other direction. They absorb heat from their environment when the reaction takes place. Those are just some indicators. Here's one example. You drop a 9-volt battery in some water, and you usually have to add a little something to conduct, like some salt or maybe a little bit of acid, because pure water is a non-conductor. It will not conduct electricity unless you get the voltage high enough. And if you do that, then you're ionizing the water molecules and you can conduct a current. But usually you have to add it yourself. In this case, I've got a 9-volt battery with a positive and a negative charge, and on each terminal, you get the production of gas. So what's happening there? Well, the only reactant in there is water, right? So something's happening to water. And to make a long story short, one terminal produces oxygen gas and the other produces hydrogen gas. So if you look at the formula for water, it's producing hydrogen gas and oxygen gas. This is your liquid. And have I explained that to you guys yet, the parenthetical phase indicators? Okay. So in this case, we see a gas forming, and that indicates that there's a chemical reaction going on. Okay, so we get those bubbles. And if you have a way to separate, like if you had a real small test tube, you could submerge it. You'd have to fill it with water first and submerge it over the terminal. You could collect that gas, and then since hydrogen is lighter than air, you could just pull the tube out and keep it inverted. You wouldn't lose any, not much. Then you could take a match or a lighted an amber and put it close there, and it would pop, because you set off the reaction between hydrogen in your tube and oxygen in the atmosphere. And you get the reaction would go back the other direction. You get your hydrogen plus oxygen, and you produce water. So the reactions can go both directions. So in this situation, we're adding something to a flask, and we're getting a color change. We're going from pink to blue. So the reaction itself is not critical at this point to understand that a reaction has taken place, and we see a color change. In this case, we're adding two solutions together. This one we're pouring into this clear solution here. And when they contact one another, the reaction produces a yellow solid. We call it precipitate. So that also indicates a reaction is taking place. Okay. I think I've got video coming up here in a few minutes, so I'm going to be sure this is turned on. All right, so how do we write a chemical reaction? It's a symbolic representation of what's going on at the microscopic level. And we always write the reactants on the left-hand side. Whatever they may be, separated by plus signs. So you have something here maybe. And then an arrow. And you have products on this side. And it might be something separated by something.
Is the arrow usually like the universal thing for a chemical reaction?
That's what we use in chemistry. Yeah, we just use the arrow. We never use an equal sign. It's always an arrow, because an arrow indicates going that way. Now, if we want to indicate that there's possible reverse reaction, then we just put an arrow in the other direction. And the reason we do that, rather than the equal sign, you don't know which way is which, right? It doesn't say one side's products and one side's reactant. So we use two arrows, and sometimes we indicate things that are taking place in one direction here, and what happens when you go the other direction, right? You might, in order to go from this side to that side, you might require some heat, and that's our abbreviation for heat. But a number of things can go in this area. We're not going to be too concerned with that. We're going to take it one step at a time. So the other one thing that you'll notice is that if you've got an element on this side, got to have it on that side somewhere. It may be in one location, it may be in two or more locations, but it's going to be on both sides. So hydrogen's here, hydrogen's over there, oxygen's here, oxygen shows up there and there. But it has to be on both sides. And this is leading up to conservation of mass, the law that says that the mass of everything that goes in has to equal the mass of everything that comes out as a product. So reactant mass equals product mass,
How can there's more oxygen on the right side?
because the equation is not balanced.
Oh,
Yeah, that's a good observation. This equation has not been balanced yet. And we balance it in order to obey the law of conservation of mass. The way you obey conservation of mass in a chemical equation is be sure you've got the same number of atoms of each element on both sides. So at this point, we've got the same number of carbons. We don't have the same number of hydrogens because there are 4 here and 2 there. That means we've got to go through the process of balancing the equation. And oxygen, you've got 2 here and 3 on this side. So that's a definite indicator that the equation is unbalanced. So as written, it does not obey the law entirely. It only obeys the law of conservation of mass in terms of having all the elements accounted for. But their numbers are not right yet.
Will the reactants and products always be balanced for like general like I mean, will they always be balanced if we lose any the reactants which is a reaction or whatever?
No, you have to account for everything. It all has to be in this equation.
They'll always be balanced.
You may have to balance it yourself. Right? It's not going to always be given to you balanced. So we're going to cover that. But the first thing you have to do is be certain of your reactants and products. Right? What are your reactants? Elements, compounds, and what are your products? Okay, that's why we spent so much time on correctly writing compounds. If you don't have them written correctly, you'll never be able to balance your equation. Okay. We've already covered that. Just mentioned that. Sometimes you'll have polyatomics on one side or the other. And I'll get to that. When we talk about balancing equations, I'll bring up that topic again as one of the tricks that you can use to shorten the painful effort of balancing an equation. So just store that one away for now. This doesn't help me much, but sometimes it helps a student to see it in picture form. This is an unbalanced equation as we had it written before, right? So we've totaled up 1 carbon, 4 hydrogens, and 2 oxygens on this side. 1 carbon, 2 hydrogens, 3 oxygens. So that indicates unbalance, right? If you show different numbers of each element on either side, then you know your equation is unbalanced and you've got to do something about it. Once we balanced it, we should have the same number on each side. Right? So this is what they've done is expand the equation. So we need another oxygen here. And we need another water here. But the way you write that is with coefficients, we call them prefix numbers. Those coefficients tell you how many of these oxygens you have. Here, you have an oxygen there, but we write it 2 in front of the O2. Okay, so there are symbols. Solid, liquid, gas. Did I cover aqueous as well? Okay, good. Those are the ones we're not going to be interested in any other phases, only those 4. So here's an example. Potassium, which is a metal, alkali metal. Drop it in water. So there's your other reactant. They're separated at the moment. Potassium is usually stored in oil, mineral oil, to keep it away from atmospheric moisture because it is very reactive. If it comes in contact with atmospheric moisture, the reaction is violent. So we store it underneath mineral oil and only pull it out when we need to conduct an experiment. So here's one reactant, here's the other reactant, and what does it produce? Well, it produces gas, right? Hydrogen gas in the reaction, and it produces potassium hydroxide in the reaction, which remains in solution. So this gas escapes, right? We don't have it, it's not capped, so the gas escapes, and when it reaches the surface of the liquid, it combines with atmospheric oxygen, and there we get the pop, the hydrogen, oxygen, and there's enough heat produced in this reaction that it ignites the hydrogen in the air. That's why you see that flame. Okay. So if you want to damage your neighbor's swimming pool, just get your big chunk of potassium, throw it in his pool, and it'll produce so much hydrogen gas, so much overpressure that it'll probably crack the pool. Well, it used to be, I should say. When pools used to be made out of reinforced grout of some kind, they just lined the hole with it. Now, of course, they have the plastic inserts. It may not work anymore. I might burn a hole through the plastic. There's a lot of heat produced. But this is the reaction describing it, of what is happening when we combine this reactant and that reactant. We get this product. We see the gas. We don't see the potassium hydroxide, right? It goes into solution, so you can't see it. It's colorless. But if we count up the atoms, let's see, we've got one potassium here and one there. We've got two hydrogens here, two there, and one there, so it's three hydrogens. We know it's unbalanced. So it has not been balanced yet. Okay, so if we let's take a word problem and see if we can write an unbalanced equation for what's happening. So it says when blue light shines on a mixture of, so the mixture, the reactants are hydrogen and chlorine gas. Right? So what should hydrogen be written as? That gas is combined with chlorine gas. How about that one?
Also diatomic?
Yeah, that one's diatomic also. Right, because hydrogen, nitrogen, oxygen, chlorine, bromine, iodine. Those are all diatomics. So we got our reactants. So what are the products? They react explosively to form gaseous hydrogen chloride. Or that's actually a misnomer. Gaseous hydrochloric acid is wrong. And here's why. That's hydrogen chloride. That's hydrochloric acid. It doesn't become an acid until you put it in water. So let me make a note. I need to correct that slide, because I think I've done this before and just didn't fix it the last time it happened. Gaseous hydrochloric acid. That should be hydrogen chloride. It might appear on the surface that I'm putting too fine a point on that, but it's true. So, tells us that it's gaseous, so we do this. There we go. So when blue light shines on a mixture, so what we would do here, and you don't have to remember this abbreviation, but if you're going to stimulate a reaction with light, we write this, which is the Planck's constant times the frequency of light gives you energy. That's where that comes from. So don't worry about that. That's the blue light, okay? And there we have our unbalanced reaction. Now, can we say it's unbalanced? I think so. 2 hydrogens here, 1 there, 2 here, 1 there. So we know it's unbalanced. If you wanted to balance this, it would be very simple. Right, let's put a 2 here. 2 hydrogens, 2 chlorines, 2 chlorines, 2 hydrogens. So that one was really by inspection, truthfully. We didn't have to do any calculations.
You want the 2 in front of CL. Or you need to put it on parentheses, or
No, if you put a 2 in front of a compound, that 2 propagates through the entire compound for the number of atoms. You don't want to put a 2 in here because that breaks up your compound. And your compound is hydrogen bound to chlorine. We can't put a 2 in there because there's an understood bond. Put a 2 in there, that would break the bond. So we put the 2 out here. And it means 2 of these. So we have 2 of those. We will use parentheses. Believe me, we will use them. But there's a special case for that. Okay, so there's our unbalanced equation. And we just balanced it for fun. So the whole principle behind balancing an equation is you've got to have the same number of atoms of each element on both sides of the arrow. That's it. That's the end goal for balancing an equation. Usually what happens is you're given both the reactants and the products. There are occasions where you can make valid predictions. If you're given the reactants, you can say, these are going to be the products. But they're very special cases. Most of the time, you're given both of them, and you just have to write the equation correctly. You may be given the reactants and products in verbal form, in English, and then you have to translate that name into a compound or an element. That's why we spent so much time on nomenclature. Okay, once these compounds are established as reactants and products, you cannot change their formulas. In other words, in order to balance the equation, you can't go in here and change subscripts. Like say we have, like this one. If you have calcium chloride, you know that that's the correct compound because chlorine is 1 minus charge. Calcium is a 2 plus charge. 2 times a minus 1 is 2 minus, and that balances. So once this compound is written, you cannot change the subscripts. If you do that, you've changed the compound. So the only way to balance is with coefficients. You just put a number in front, and that gives you 1, 2, 3, 4, however many of that compound you need. But the first step is you have to write the compounds correctly. Once they're written, you can't touch these. We couldn't go in here and say, well, I need 2 calcium, so I'm going to put 2 there. But I only need 2 chlorine, so I'm going to leave that one alone. You don't have the same compound anymore. In fact, that compound does not exist. Okay. So these are the steps for balancing an equation, but I think it would be more efficient to take one and just go through it step by step. and just see it done. You can go back and review this if you want. That's fine. But I think it'd be more instructive to take an example. Go backwards. All right. Let's say we have this unbalanced equation. We're given the compounds or the elements. We're given the reactants and products. We just need to balance it. So here's the way you do it. This is the way I do it anyway. You just write out the unbalanced equation and leave yourself room for your coefficients. Okay, because you're going to be putting those in there. Then let's check to see if it is unbalanced. Okay, we have one calcium. We have one carbon, two carbons, three carbons. And we have one oxygen here and two oxygens there. So it is unbalanced. So I set up a budget. We say, down this side, we put, what do we have? And we have to be sure that we've got the elements on both sides, right? Which we've established. Then you write the elements that you have here. Okay? And then under this side, you put what's on the reactant side. How many do you have? So we have one calcium here. We have one oxygen. We have one carbon. Then over here, kind of set up a table. Over here you have one calcium. We have two oxygens. Yes, two oxygens and three carbons. Okay. So this way, you know where the imbalance is. And as we balance the equation, go through the steps, we're going to change these to reflect the amounts that we have after the change. So when you get finished, these numbers should be equal. Okay, then you know your equation is balanced. Okay. So trick number one, if you have an element that's by itself, if at all possible, save that one till last when you start adding coefficients. The reason being, if it's a single element, if you put a coefficient in front of that, it only changes that one. Whereas if you put a coefficient in front of this one, it changes that one and that one. And that may affect your balance somewhere else. So save your element, this one element, to last. Okay? So let's set carbon aside for the moment. We may be forced to go to it right away, but that's rule number one. So save that one, and let's look at the others. Calcium's okay right now, so we don't have to touch it. We might have to come back to it, but right now we can leave it alone. Oxygen, we need two oxygens on this side, right? So we put 2 here. And that gives us 2 oxygens, but it also gives us 2 calciums, right? Okay, so now oxygens are balanced and calcium's not. So we go over here and look at calcium and say, all right, what if I put a 2 in front of this calcium? That would give us 2 calciums here. But it would give us 2 times 2 is 4, plus 1 is 5 carbons. Okay, so now we have our calciums and oxygens balanced, but the carbons are not balanced. We've got 5 carbons on that side, we need 5 on this side. So there's our carbon sitting all by itself. All we have to do is that. And now it's balanced. 2, 2, 2, 2, 5, 5. And then you can go check yourself. But this should be sufficient. I mean, if there's balance there, you should be right up there. Now what you want to do is look at the coefficients. Can we divide all of the coefficients by a whole number and reduce their values to whole numbers? Kind of like least common denominator. Well, no. Because you've got an even and an odd, there's no way you're going to be able to divide by the same number and reduce it. The reason you look at that is the accepted convention is you want the smallest whole number coefficients for your entire equation. That is to say, technically speaking, oh, I must have accidentally punched the button. Technically speaking, 4, 10, 4, and 2 would also be balanced. It would just make this one 4, that one 4, and this one 10. If you doubled them all.
How do they get this?
If you take half of this, so as long as you go, in some respects, chemical reaction equations behave like algebra. If you take that whole equation and divide through by a number, you've still got the same ratio of reactants to products. So if you divide by 2, that's 1, 2 1/2, 1, and 1/2. So that would be true, but it's not convention. Convention is the smallest whole number coefficients. So what we want, those are all possibilities, right? But which is the best one? This one right here, right? If we take this one and divide it by 2, divide that one by 2, divide that one by 2, divide that one by 2, and divide that one by 2, you get this equation. Okay, so that's the preferred equation, 252. And don't forget that there's an understood 1 here. If you've got the compound, you don't have to write the 1. But if you've got the symbol for the compound, you got the formula for the compound, you got to have at least 1. Otherwise, there's no sense in writing it. We wouldn't put a 0 here, because that means it doesn't exist. So don't forget that 1. The reason I say that is some exam questions may come in the form of, when this equation is balanced, what is the sum of the coefficients? So you'd add them up. 2 plus 5 is 7, 8, 9, 10. Don't forget that 1. Okay, just a word of warning. Okay. Which one of these statements is false? Well, let's see. Subscripts in the reactants must be conserved in the products. Well, let's take this one as an example. We balanced it, so we don't need to keep this anymore. So let's look at it. Subscripts in the reactants must be conserved in the products. What's the subscript for calcium? 1 and 1. Well, that's not a good example. Oxygen is 2. So A is false. You do not conserve subscripts necessarily. No, you do not conserve them. That was a coincidence. Just because this one is 1 and that one's 1 has nothing to do with balancing the equation. It has everything to do with writing the compounds correctly. Because what's the charge on oxygen? 2 minus, 2 plus, 1 and 1. Charge on 2 plus and carbon in this case is is going to be, well, we have to decide what it is. Carbon is one of those. Remember that's in this family right here? You're okay over here and you're okay over there. When you get the carbon family, all bets are off. It can be all over the place. Right? So you can't say what the charge on carbon is except by deduction. So we would say carbon in this case would be a charge. This is 2 plus. And you got 2 of those, 2 minus total, then each one has to be 1 minus. Okay? Did I lose you? Okay. I look for visual cues. If I see a puzzled look, then I want to find out if the train's getting ahead of me. Okay, so A is false. Coefficients are used to balance the atoms on both sides. That's true. You always use coefficients to balance the number of atoms on both sides. When one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. That's true. If we've got a balanced equation and I double this one, I better double everybody else. Because what you're establishing is a ratio. For every 2 of these, you need 5 of those. And for every 2 of these, you produce 2 of those. Or you produce 1 of those. For every 5 of these, you produce 2 of those and 1 of those. It's all that ratio that's important. So C is true. D, phases are often shown for each compound but are not critical to balancing equation. That is true. Balancing the equation is just numbers. The phase is useful information when you write the equation sometimes, and hopefully we'll get to the point where I'll bring that topic up again. But for balancing the equation, all you need is numbers of elements in each of the reactants and products. So that's the only one that's false. This is just to hammer that point. You got to have the same number of atoms of each element in the reactants as you do in the products. Can't change the subscripts. Once you've written your compounds and elements in their proper place, reactants and products, can't touch them. If you touch them, they'll burn your hand off. Just put that mental image in your mind. They're too hot to touch. Don't touch the subscripts. So a balanced equation tells us the ratio of the number of molecules which react and are produced in a chemical reaction. That's true. Number of molecules and or elements. But sometimes you have separate elements, okay? Not molecular. But for as far as it goes, that's a true statement. It's all about the ratio. Well, coefficients can be fractions, but we prefer the lowest integer. For now, that's the rule. Like the smallest possible integers that maintain the ratio of reactants to products. I don't think we're going to get to a point in this class where we need to use fractionals. Oh, except for one trick. I'll show you that one later, where we use fractionals as an intermediate step. I thought we were going to do more of that. Balancing equations. Maybe we get to that in the next chapter. I think we need to do, or is that coming late? Chemical quantities? No. Let me see. I handed out the review document. Wait a minute. You didn't get a copy. You need to take the exam too. This is the next chapter. We're not on that one yet. And here's the review document. Okay. So at let me see in the useful information that I give you. Yes. I included it in the useful information this description right here. This gives you helpful hints for balancing equations. And that I should eventually incorporate that into the slides. But we need to talk about that. So let's do that before we move on to stoichiometry. So here's a sample equation. I'm going to use that one at the bottom. Let's see. No, let's not use that one yet. Let's use, let's burn octane, gasoline. How about that? So C8H18, that's octane, the principal component in the gasoline tank. Now there are other things that are added along with it, but that's mostly what it is. And in fact, pure octane sets the standard for the NOC rating. 100 octane is octane rating is 100% octane, how it behaves in an engine. So we're going to burn it, right? Have to add oxygen. And what does it produce? Well, if the reaction goes to completion, which is another topic, in your engine it usually doesn't. It leaves some pollutants, and that's why we have catalytic converters. But that's another topic. But if it goes to completion, it makes carbon dioxide and water. Okay, so in this case, you're given what the reactants are. Burning octane means you're combining it with oxygen. And you're producing carbon dioxide and water. Okay. So if we set up our table to see, we've got carbon, hydrogen, oxygen, carbon, hydrogen, and oxygen in 2 places. So we want carbon, hydrogen, and oxygen to balance. So how many carbons do we have here? We have 8. How many hydrogens? We have 18. That's why they call it a hydrocarbon. You've heard that term before? Hydrocarbons? No? Okay, you have now. And oxygen. We have 2 oxygens because it's diatomic. And on this side, we have 1 carbon. We have 2 hydrogens. And we have 3 oxygens. Okay, that's obviously unbalanced. So, do we have any single elements isolated on either side? Yes, you have oxygen as a reactant. So we're going to save that one for last. And if you do enough of these, you get a feel for where should you start first. But if you don't know or don't remember where to start, just hold that one out and start with the first one. So if we've got 8 carbons here, we want 8 carbons here. That gives you 8. But it affects the number of oxygens too. So we have 2 times 8 is 16, plus 1 is 17 oxygen. Okay? How about hydrogens? Well, we've got 18 hydrogens here, and we've got hydrogen here, and this is the only place it occurs. So we can say 9. 2 times 9 is 18, right? That gives us 18 hydrogens. I'm sorry?
We just add a minus.
No, you have to recount from scratch. You can't just add it to this. You got to count from up here. So we have 16 oxygens plus 9 oxygens. 25, right? Okay. So now we've got carbon and hydrogen balanced. We need to balance oxygen. The problem is we need 25 of them over here, but this is an even number. So what are you going to multiply by 2 that gives you 25? Multiply by 12, we get 24. By 13, we get 26, right? So here's another shortcut, a rule, a hint, a trick. Use a fractional coefficient, just as an intermediate step, right? So if we say 25 halves, that will give us 25 here. How do I know that? Because 25 halves times 2 is 25, right? Multiply 25 like that times 2, and you get 25. Okay? So now that we've got it balanced, we want to get rid of that fraction. So how do you get rid of the fraction? Multiply the whole thing through by 2. Right? The ratio has already been established. We've balanced the equation, so we have the same number. We have the ratio of this to that, to that, to that is established. Right? So now we can multiply or divide through by any number, and we have not changed the ratio. So 2 times this one would be 2. 2 times this one would be 25. 2 times this one would be 16. 2 times that one would be 18. Okay. Now we're balanced with the smallest whole number. And then you can clean it up if you want to. So if there's a question on the test that says, what's the balanced equation for these reactants yielding those products? And there'll probably be a line there blank as a short answer, and then you just write in. But there'll be plenty of room below that for you to do all your work. Then you just put the answer in on the line. I think there's a couple of examples. Yeah. Like, short answer work. Okay. So that gives you hold out single elements for last. If water is a choice, try to hold water out to last too, but that varies. Fractional. Oh, and then this is a useful one also. Let's do the one at the bottom of that page. So let me write it in unbalanced form. Ammonium phosphate, one of the reactants. So you know it's going to be ammonium with phosphate. Okay? So phosphate, these are both polyatomics. This one is a 3- charge, and this one is a 1+ charge. So with polyatomics, remember you have to write them with the parentheses. So we do this one like that. Put a 3. 3 times a plus 1 is equal to 3 minus. Okay. So that one is going to react with calcium chloride. Okay. The -1 for this one times 2 is 2 minus, and it balances calcium with 2 plus. So that one's written correctly. Now, what are the products? The products are calcium phosphate. Right? So there's your polyatomic with a 3 minus charge, 2 plus here. So how do you get that one to balance? Of course, multiply. So you need 2 of these for that one, and 3 of these for that one. And that one's written correctly. 3 times 2 plus is equal to 2 times 3 minus. Okay? And then the last reactant is, product is ammonium chloride. Ammonium chloride. This is a polyatomic with a +1 charge. Chlorine is -1 charge. So that one is written correctly. Now we want to balance this equation. Here's the last hint. If you've got polyatomics in your equation and they remain intact on both sides, in other words, there's your ammonium, here's your ammonium. It has nitrogen and hydrogen in it, nitrogen, hydrogen, and it's not broken up. In other words, that nitrogen doesn't appear anywhere else. As long as it remains intact, you can treat it as a separate element in your table. So we would put like this, would be one of the balancing elements that we put in. Phosphate's the same way. It's not broken up in the process. And by implication, I'm saying that some reactions will take that phosphate and tear it apart. In that case, you have to go element by element. But if it maintains itself on both sides, you can use it as a balancing element. Okay, and we've got calcium and we've got chlorine. We've accounted for all of our elements and polyatomics. This saves you a lot of headache. Instead of writing nitrogen and hydrogen separately, phosphorus and oxygen separately, since they remain intact on both sides, it's fair to use them as separate balancing elements. Okay? So now we do our tally. So we've got 3 ammoniums, 1 phosphate, 1 calcium, and 2 chlorines. On this side, we have 3 calciums, phosphate, 2, 1 ammonium, and 1 chloride. There we go. Now, we can see at a glance that that equation is not balanced. But the first step we went through was correctly writing the equations. The compounds. Get their formulas right. If you can't make it past that step, then you'll never balance. Okay, so we've tallied what we've got first, and there are no free elements in here, so there's nothing to hold till last. So I would just start at the beginning. We've got 3 ammoniums on this side. We need 3 ammoniums on this side. Okay.
But you're going to have to change it.
I'm sorry?
You're going to have to change it because you need 2 phosphates right over there. So it'll be 6. Right.
I got 3 ammoniums here. I need 3 ammoniums there. And that changes 3 chlorides.
before on the right B.
Yeah, I was
It
saying
raises.
that you're gonna have to put a 2 in front of it because phosphate needs 2. So then it's gonna change to 6.
I haven't got there yet.
That's what I was gonna say, you might change as you go.
Yeah, oh, yeah. Yeah, we're gonna get there. We have to be sure that we accounted for the change here, 3 and 3. Now we'll have to go back over here and write with 2 phosphates here. But that gives us 6 ammoniums, doesn't it? So if I go over here, I have to change this to 6. That makes this 6. That makes this 6. Now, we'll see how many calciums we've got. We need 3. 3 calciums here, and that gives us 6 chlorides. Looks like we're balanced. So our coefficients will be 2, 3, 1, and 6. Like I say, don't forget that 1. All right.
Why is the ammonium on the right side?
Why is it not in parentheses? Because in the compound, there's only one of them. You don't have to put a parentheses around it if there's only one. If we had 2 of them here, yeah, you would have to put a parentheses and then a 2 subscript. Any questions? Okay, so as you're practicing balancing equations, you can always look at this to help you go step by step. Now that we've got a balanced equation, what do you do with it, right? Because this is not the end of the story. Once you have a balanced equation, you have a way to tell, let's see, let me change this to 6. Right. With a balanced equation, you have a way to tell if I start out with a certain amount of this, how much of that will it produce? That's stoichiometry. Well, that's also stoichiometry. Use your balanced equation to determine the relative masses of reactants and products. Now, I want to hammer this point hard. When you look at this equation, what are you seeing? You're seeing a representation of molecules. Like 2 molecules of that with 3 molecules of that makes 1 molecule of that and 6 molecules of that. We said nothing at all about mass, only numbers. Okay, so many numbers of this plus so many numbers of that makes so many numbers of this and so many numbers of that. Now, what I just said was true. Molecule, 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 molecule. But it also works for any other measurement of numbers. For instance, moles. 2 moles of that plus 3 moles of this makes 1 mole of that and 6 moles of that. Okay, the ratio is the same. We're just using a different unit of measure. Instead of individual numbers of molecules, any individual molecules, we're using a large number of molecules. 6 times 0.022 times 10 to the 23rd of them. In this case, twice that number. 2 moles, 3 moles. So the ratio is established in terms of numbers of atoms, molecules. Okay, but that doesn't mean you can't use it to determine mass. Because we don't weigh things in terms of molecules, we weigh them in terms of mass. And if you're given a certain mass of this reactant, can you tell how much of that would be produced if all of it were converted? Yes, you can. But you have to take the mass of this and convert it to moles. That's why we spent so much time on unit conversion. Mass of this, you can tell how many moles it is. You need the molar mass of that compound. And you can convert mass to moles. Once you have the number of moles here, then you can use the ratio of this one to that one to tell how many moles of that one are produced. Okay? Once you know how many moles of this one are produced, you can convert back to mass using the molar mass of this compound instead. Okay? That's stoichiometry. Okay. Well, let me see. I'm confused and perplexed because I thought we were going to do more. Chemical quantities. Oh, okay. Chapter 9. Chapter 9 is where we get into chemical quantities, and then we do just what I was talking about. Convert mass to moles, then migrate to another part of the equation, and find out how many moles are produced, then convert back to mass. So let me see. This review, chapter 6 and 7 review, is going to be on balancing equations and coefficients. Okay. Types of reactions. We didn't get to that. We're going to get to that here. Yes, we are. Okay. All right, just checking. Chapter 7 is going to finish it out for us. So you can go through here. I think they're ordered in sequence, but you get to a point. I think I just saw it. Here it is. Okay, so chapter 6 is up through page 25. Okay, and then past that is chapter 7. All right, so if you want to work on between now and Tuesday, we could get into chapter 7 if you want to.
Can I get a copy?
Oh, yeah. Oh, oh, there's 6. There's 6. I ran out of review document here. Oh, that's because I took it out. There you go.
Thank you.
Let's see. Maybe it would be good to get into chapter 7 a little bit. Okay, so let me, I'm going to stop this one. Unless anybody has questions about chapter 6 and what we've done so far. Okay, I'm going to stop this one. I'm going to start a new one with chapter 7. And we'll partially get into that one, which means I'll probably hold the chapter 7 until we finish it next time we meet, before I post it with what we finished. Does that make sense? I'm only going to put 6 up on Blackboard by this evening, but I'll hold 7 until we finish chapter 7 next time we meet. So let's